of space will be the region for the integration, and as usual, and in that region either a scalar function or a vector function will be defined at each and every point inside as well as on the surface of that region V, three-dimensional region V. And now this region we will divide into different parts. You look at the figure, we will divide into different parts, smaller parts, and each part will be a three-dimensional, very small, tiny region, and which we call that region as delta Vx.
Sir, you are muted.
You're muted.
Sir, anyone muting?
Sir, you are not audible, sir. Sir, you are not audible.
Yeah, someone of you. Yeah.
Yes, sir. Again, you have to change the settings.
Sir, take control in your hand.
Someone is muting you, sir.
Yeah, someone is muted.
Again, you are muted, sir.
Sir, you have internal meeting. You will not find the settings, I think.
Sir, that's why we were saying that you should take your class in your own channel because you are the owner there, I think.
Yes, sir.
Yes,
Yes,
Sir,
sir.
okay,
But
sir.
what
Yes,
will-
sir.
schedule the class, sir.
Sir, continuously
Your time
muting
is also available.
all the presenters, sir.
Yeah,
Sir, please
so
schedule this.
yeah, some friends of you are taking fun of it. Yeah, fun of this.
We have that tab, sir. We can identify that.
Person.
Sir, here.
Sir, again, you are.
Again, sir. I have a app. I can
Sir,
identify that voice, sir.
Yeah, so better I appeal to their good sense. Don't do this. Okay. If you are not interested, then fine. You can skip the class. Okay, but don't disturb the system. Okay.
please reschedule this class.
Sir, from next time, na, you take your class in your channel, sir. That is be fine.
Okay, I will do that. But today almost. Okay, so let me.
Yes, sir, you continue.
Yeah, let me continue. So basic idea is similar. You see the region has been changed and the entire region is divided into different small parts, and now the parts will look like a tiny three-dimensional region. Okay, a portion of space, and a typical portion of space we'll call it as delta Vk, and from that region it will be a parallel rectangular parallelepiped having dimensions delta xk, delta yk, delta zk, and from that region we'll take a point, and at that point we'll calculate the value of the function, whether vector or scalar, and then we'll form the sum and we'll fill the entire region. Okay, that can be done approximately done by considering very small rectangular parallelepiped type of region, and if the limit of this sum exists, it is called the volume integral. Okay, so probably it has already been discussed in the triple integration class. There is no difference. Only thing is that probably the introduction of this vector function, but the basic idea is similar if you think component wise. If you think component wise. Yeah, so and it is denoted by the volume integral is denoted by a dv, and this is equal to limit of this sum. Now yeah, so if you have any question, so I will not discuss any problem today, any more problem today. If you have any question regarding the idea, basic idea of integration, you can ask me, so I'll be happy to respond.
Sir, the difference between triple integration and volume integration?
So essentially it is similar. Okay, triple integration and in triple integration what type of region has been discussed in your class? Region of integration, is it always taken as rectangular parallelepiped type of region, or any general three-dimensional region has been
Yes, sir.
considered?
Circular form and cylindrical form.
Yes, sir.
Always in rectangular, but it can be extended to a general region. For example, inside the sphere,
Yes, sir.
Okay.
Sir, spherical form and cylindrical form.
Yes, sir. Spherical and cylindrical were the two
cylindrical-
concepts which have been discussed.
Yeah, that also has been discussed, right? So therefore, in that sense, volume integral and triple integral are not that much different. And basic idea probably you could understand. That is my feeling. If you think little bit, and the main idea has been translated from the function of single variable in the idea of integration, definite integration as a limit of a sum for the function of single variables. So same idea, we have a region of integration, and in that region a function is defined, scalar function for the simplest case, okay, for which you have solved many problems. Okay, so that has been discussed, that has been defined as a limit of a sum, and if you remember that formula is h into f a plus rh. Okay, so what is a plus rh? A is the left hand point of the closed interval and B is the right hand point of the closed interval. Okay, so and that entire interval, closed interval, we divide into finite number of parts, and in each part, finite number of parts, in each part, from each part we are taking either the left hand endpoint or the right hand endpoint, and at that endpoint we calculate the value of the function, and that value of the function is multiplied by the width of that associated subinterval. That is your integration element there, and you are adding such elements for all the subintervals, and then finally you are taking finer and finer partitions, we call it finer and finer partitions. That means we are introducing more and more points within that interval, closed interval, and that is basically the limiting process. And in the limit, if the value of that sum approaches a finite number, then that is called the definite integration. So now whatever type of integration you define, okay, what will be the changes? Only the region of integration will change. It can be quite arbitrary, like it may be a portion of a plane, it may be a portion of a space, or it may be a portion of a surface taken in 3 dimensions, or you can even define it for higher dimensions as well. There will be absolutely no difficulty. Only thing is that we have to clearly understand the region of integration as well as the function involved in the process. Function can be quite complicated, or in sometimes there might not be any formula. Okay, you may have some experimental value. You don't have definite formula, but you know the value of that experimental measurable. For example, intensity of light. You may not have some formula, but you know the number at different grid points or at different sample points. You can use that numbers to define your integration. So what we have to do, we have to divide the region of integration into different parts, and from each part we have to take a point, and at that point we have to associate somehow a vector or a scalar. Okay, if you associate a vector, and associating a vector also we can generate a scalar, the way we have done for our surface integration, a particular type of surface integration we have introduced over here. That is f dot n. We have taken the normal component while defining the surface integration. Okay, and we can keep the vector as well as it is. So vector into the if you consider the surface integration, you can multiply it by the area of the tiny region you are considering, or if you are considering the volume integral, you can consider the volume of that region. So that will be your integration element, and then we have to take the sum, and finally we have to take the limit. So that is the basic procedure, and if we understand this, there will be, I believe that there will be no difficulty in understanding any kind of general integration. Okay, and I have discussed some problems, and some of the other problems will also, some more problems will be discussed in the tutorial class. That are taken by Dr. Debashish Ghosh and Mrs. Bajaj. So they will be taking the tutorial classes, and there also some more problems will be discussed. As far as theory is concerned, if you have any difficulty at this moment, you can clear your doubt for today's class. In today's class, yeah.
Sir,
Yeah.
I have a doubt. Can you please in surface integral second
Yeah.
problem.
So please one by one. Yeah.
Can you please share the PPT that you were teaching from today?
Yeah, it has been already uploaded.
Sir, where is it uploaded? I couldn't find.
It is in the
Channel.
Yeah, it is in the channel, and I have also uploaded 3 problem sets.
Channel in the file section.
In the file section, yeah. 3 problem sets are there, and all the so there are many problems you can see. Better if you can solve most of the problems. Okay, so I think then the integration related thing will be clear to you once for all. Yeah.
So in surface integral that you have given 4 sums, no sir. In that second one, can you please explain it?
Surface integration.
What we have to take n bar the f bar dot nds, no sir.
This one, this second
Yeah.
one. Yeah.
Yes,
So yeah, let me tell you. Let me show you. I have some
Can
time.
I solve this by divergence theorem?
Yeah, divergence theorem, you can solve it. Very good. But I have not discussed it yet. So I thought I will discuss it tomorrow. Let's see. So this one, let me just focus on the region.
Sir, you are muted, sir.
That you are muted, sir.
Sir, you are
Again, you
muted.
are muted, sir. Sir, you are.
Yeah, please don't do this. Okay, at least for next 5 minutes to 3 minutes. So let me just discuss the region. Region of integration and how to find the surface integration. Yeah, so let me show you. Yes. Okay. So this is zero x y z. Okay, so this point is 1 1 0, and you divide the entire surface. You divide the entire surface into different parts. For example, this is your S0, the portion of the XY plane. A, B, C, D, E, F, G. Then S0 is OA, BC. S1 you take, S1 is this, say Z is equal to 1 plane. S1 is equal to DEFG. DEFG. S2 is the front surface. This is S2, and the back surface is S3. So this is equal to ABEF. And S3, this is the back surface, that means OCDG. OCDG. And this side, right hand side, S4. S4 is this one, and S5 is this one. So S4 is BCDE, and S5 is OAFG. FG. Now the surface integral, whatever function is there, forget about it. Yes, so basic idea I am telling. This is your surface is the total closed surface bounding the unit Q, and that you divide into 6 parts. S0, this one ds plus S1, this up to S5. Now on S0 there are some simplification. We are on the XY plane and Z is equal to 0. Basically on S0, Z is equal to 0 and dz is also equal to 0. Z is not changing. and you will have only dx dy. Your ds will be equal to dx dy. Okay, so therefore you can calculate this surface integration on S0, and on S1 what will happen? Z is equal to 1 and dz, that is equal to 0. And what is your ds? ds will be equal to, it is on the plane, we are on the plane parallel to xyz, xy plane, therefore ds will be dx dy. So this is how for, and then on your S2, what will be the simplification? S2 means which plane? ABEF. ABEF, the front plane. On this front plane, x is equal to 1, you see, and therefore dx will be equal to 0. And your ds will be equal to dy dz. So this is how you have to simplify, and you have to calculate all the surface integrals, and you have to add. Okay, still if you have problem, if you cannot solve, I will discuss it in the next class.
Sir, if suppose the surface is not exactly, if the surface is not exactly parallel to any xy plane or xz plane, then how will we decide?
Then you have to take the projection n dot k, or you have to take the projection of the surface on an appropriate plane. Okay.
So please stop the recording.